back to this NPTEL online certification course in molecular rearrangement and reactive intermediates. In the last couple of classes, I started talking about different type of organometallic reagent. I talk about organolithium, the Gigner reagent. Then I talk about organocopper and organozinc reagent. In the today's class, I am going to start talking about the p block elements. The first I am going to talk about the boron, and then followed by the silicon and others. So in this class, I am going to start about the discovery of the boron, and then some of the different compound of organoboron reagents, and then what is the structure. We can compare their stability, and also at the end I am going to talk about some of the synthesis of the organoboron compounds. So here the first thing you have to learn that organoboron compounds are, so this is a p block elements. I think all of you familiar with that, with atomic number 5, and it is a metalloid element, and it is not very much abundant. So it is a low abundant in the earth crust, and also it is found as a water soluble borate minerals. So you will see that several type of borate, the boron has several type of borate minerals. There you can find some of the organoboron compounds. But our interest going to the boron based compounds. The first thing is the element boron was discovered by Joseph Louis Gale Luzac in 1808. Okay, you can see what is the reaction happening is a reaction of potassium and with the boron oxide, which actually what is happening, this from the B2O3 it is giving the elemental boron. Okay, so this is the picture of this. You can see it's a impure amorphous products with a with a black color. And then after that discovery, the this pure crystalline boron can be also prepared by another method, starting from this BCl3, okay, with hydrogens in a electrically heated tantalum filament. So if you take that, the BCl3 in a silent electric discharge, it can generate the boron as well. So now we are going to learn about the different type of nomenclature of organoboron compounds. Okay, so this is the discovery of boron, but now if you see the borons are trivalent, that means you will find out there will be 3 different groups attached with boron, and very soon we are going to talk about that the boron has a sp2 hybridization. So that means it has a planar geometry. So if you have the boron with the 3 hydrogens, I think you are very familiar with that. This is called a borane, correct? You have must heard about the lot of reactions using borane. And now if you see there is a 3 alkyl group, if you replace this H with alkyl group, this is called triethyl or trialkyl borane or triaryl. So you can see this as a, you can tell this Br3 and R is alkyls, correct? Or if it is a 3-phenyl, we can then there are of course we can have a alkyl and aryl, but let's talk about only alkyl for now. And now if you remove one of the alkyl group from here, suppose you have this triethyl borane, correct? So you replace one of the alkyl group by a OR, means with oxygen. What is happening? You are synthesizing something called a borinic esters. So now you can see we have introduced a oxygen with a R group. Okay, so that's not, and then if you have a OH here, we call it a borinic acid. If you replace this ethyl by a OH group, we call it a, so that means the boronic acid is with a boron with a 2 alkyl group with a OH group, and the boronic esters are boron with 2 R group or 2 alkyl group with the OR. Now if you replace another ethyl group with a OH group, then you end up making a boronic acid. So there is a difference between a borinic versus a boronic. Okay. So now you can see very similarly, if you have replaced in case of the esters from this side, if you replace one of the R group, you end up making a boronic ester. Okay, so these are the things you are going to see that most of the things we are going to discuss about this boronic esters and the boronic acids, because you can see these are going to be the more stable form, because you have 2 oxygens, so they are they are filling some of the vacancy in the boron, because you have a vacant orbital. I am going to discuss all of these things, correct? Why the borons are so reactive, and a lot of other things from there. And then once you replace here, let's we are still continuing it after the boronic acid or boronic esters. Now if you replace another R group, which is the last one, using another OR, we call it a borate. Okay. Or if it is just a OH, a very simple compound called a boric acid, okay, used for a lot of different purpose. So you can see these are the most stable form of the organoboron, the boric acid and the borate. Of course, there are other things which are the potassium, the borate salt and other things we are going to discuss also then. You can see here there is other type which I was telling you, that if you have the borane, which we just now I mentioned, although it's not going to stay like that, or there should be some sort of a it could be a dimer, or it could be some sort of a Lewis base will be attached with it. So if you take a H minus and add into it, it will going to form something called a borohydride. Now you are getting familiarized with this, which are used as a reducing agent, correct? And now if you replace this R group with a halogen, let's replace with a halogen, then you end up getting a monohaloborane. Now if you replace with two R groups, those are called dihaloborane, and finally if you replace three of them, it's called boron trichloride. This is another familiar compound. I am sure you guys have heard about this BF3, BCl3, BBr3, correct? Acting as a Lewis acid. We are going to come back to that discussion as well, okay? And now once you have this boron trichloride, now if you add AX there, then that will become a trifluoroborate. Okay, so you end up making a trifluoroborate from the boron trichloride. So these are the some of the nomenclature, but not only the boron can be a single boron unit, it could be a two boron unit called a diborane. Okay, or if you have something like that, if you have a two acid group attached with it, we called a so these are bisboronic acid or a bisboronic ester. Okay. Again, this is that way if you think about diborane, but exactly once you come to the diborane, which is this could be a bisborane. You cannot say diborane, because diborans are a compound we are going to discuss in a minute. We will have a structure like that. So we are going to come back to that discussion again when we talk about B2H6. Okay, we are going to come back to that. So these are some sort of a bisboronic ester or bisboronic acid. Okay. So now if you talk about the, so I think before I talk about the organoboron chemistry, I always try to give I think the credit to these two gentlemen who received. Of course, there are a lot of players in this area, but William Lipscomb who actually discovered the extra structures of the diboron, and he also solved several other extra structure of carboborons, and also developed several other things for the theoretical part for the structure of and the bonding of the diboron, and many other contributions. He received the 1976 Nobel Prize in Chemistry. And then another gentleman, Professor Herbert Brown, also awarded Nobel Prize in 1979 for his discovery with several with organoboron reagents. One of the important contribution, of course, the hydroboration reaction. So as I mentioned about these things, about the Lipscomb discovery about the carboborane. So these are the definition of carboranes. So these are the carboranes are electron delocalized non-classically bonded cluster composed of boron, carbon and hydrogen atoms. Of course, I am not going to talk about this more, just try to give you an idea of what is the structure of carborane, because you can see the borons are electron deficient. I am going to come back in a minute about their bondings, and you going to realize that borons are electron deficient, that is why they form clusters, and then this type of clusters with carbon, boron and hydrogen called carboranes, and they are one class of heteroboranes, and they can have different type of class depending on the size. They could be classo, nido, arachno and hypo. Okay. And then you can see they are the structures here. I am going to show you, and in a minute I am going to show you how this nomenclature came. So if you see, these are the closo, okay, which is the B6H6 2 minus, and then once you remove the one of the vertex from here, this is called a nido, and then once you remove the another vertex from here, this is called a arachno. But again, I think we are more interested of this organoboron chemistry in terms of the formation of carbon-carbon bonds. So the other important perspective about the organoboron compounds is that some of the, as I mentioned, the boron is a low abundant element, but the boron is also present in a natural product. That is also another interesting thing, that the boron is present in a natural product, an important compound called boromycin, which is which is an antibiotic. Okay, it actually acts as a ionophore and causes the collapse of the potassium gradient, okay, across the bacillus membrane. Okay, so there are also other compounds which was synthesized, like something like tavaborol, which has which can use for the some sort of a skin disease, and also there are anti-cancer agent called the borzomib, which was synthesized, and it was right now in the market, which is used as an anti-cancer agent. And then of course the boron is also useful for a lot of the biological study, which are where they are finding that enzyme can bind with the boron, as boron has a vacant orbitals, and it can also go for enzyme inactivation. So this is also getting studied. And again, you can understand that so there are a lot of discovery going on where people are introducing boron into the drugs to find out the improve the efficacy and find new mode of activity. So as I mentioned about the different structures of the organoboron, there are these boranes, the boron trihalides, boronic esters, boronic acids, then the borate, and then the trifluoroborate. As I mentioned that once you go in this direction from borane to boronic esters, you are getting the stability getting increased. Okay. So the question comes, why the stability is getting increased once you go from the borane to the borate? Okay. So these questions, if you try to answer, then you have to go to the hybridizations of the boron, and if you see the electron configurations of the boron, it has this 1s, 2s, 2p. I think you guys are very familiar with that. But once it is forming the sp2 hybridization, now you have these 3 sp2 orbitals. Okay, so there will be a there will be a 2s, and then there will be sp2. So once they combine, there will be 1 p orbital which remain empty. Okay, so this p orbital actually remain empty. So that's why the boron can be, you can think about that like a similar to a carbocation. We're going to come back to that discussion in a minute. So that's why, because of this empty orbital, if you think about boranes, it always hold which is combined with some sort of electron donor, means some sort of a Lewis base. So it comes as a adduct. Once you buy this boron in Sigma Aldrich or other website for your reaction, it is comes with THF or with with ammonia. Okay, because it forms it gives the lone pair to the boron and then forms a adduct. That's why this monomeric borons are getting stabilized. And these are the bonding of the boron, you can see here. So this is a scenario of a unhybridized, where you have this 1s, 2s, and the 2p orbital. There is 5 here, and then once you come to the hybridizations with the 3 groups, now there will be formation of these 3 sp2 orbitals and the p orbital which is remain empty. Okay, so there will be 3 sigma bonding here. Okay, well, once it is in the BH3, it is forming the 3 sigma bond with this 3 hydrogen atom. Correct. So now if you try to look into the the geometry of a carbocation, I think I talked about carbocation at the beginning when in this course, and if you remember that I talk about at the beginning, from methane through a heterolytic cleavage, if you generate this methyl carbocation. Now if you try to go through the structure, you end up finding very similar things. It's a sp2 hybridized and having a empty p orbital there. Okay, you can see that there will be so that means what we are trying to compare, we are trying to compare that the boron reactivity is very similar to the carbocation. That means they are electronically deficient. So any nucleophile or any having, it can attack here, or something having a Lewis base having a lone pair, they can also attack to this empty p orbital. Okay. Again, this is the orbital view of the diboron. If I think I just mention about the diboron in a one two slides before. So this is the structure of diboron, and this is the orbital view for them. So what is happening here? They are forming, okay, a 3 center and 2 electron bonds. So we have 3 center 2 electron bond. You can see there are 3 center, but there are 2 electrons. Okay, that's why. So we call also this type of bonds as a banana bond here. Okay, these are the 3 center 2 electron bonds which is forming in the structure of the B2H6. And this is the the MO of the diboron. So here you can see these are the sp3 hybridized orbital of 2 boron atoms, and these are the atomic orbital of 6 hydrogen atoms here. So we are talking about the boron and the hydrogen here. So this is the boron here, and these are the hydrogens. So you can see what is happening here. From these hybrid orbital they are forming. So there will be a sigma terminal bond form. So there will be 4 sigma terminal bonds. So these are the sigma terminal bonds, 1, 2, 3, 4, and then there will be a bridging bond between the 2 boron. So these are the 2 bridge bonds here. There are 2 sigma bridge bond formation happening. Okay. So now we are going to talk about some of the important aspect of the organoboron chemistry, like the synthesis. Okay, how to synthesize this organoboron compound. So the first thing, discovery Alfred Sock first obtained the mixture of boron in low yield when he treated the magnesium bromide with the hydrochloric acid, with the magnesium borate with the hydrochloric acid. So once you treat the magnesium borate with the hydrochloric acid, it generates the B2H6. Also it can be prepared from the sodium borohydride. When it is treated with the I2, it is also generated the B2H6. Okay. So this is about the boron, and then the synthesis of the trialkyl boron can be done through the hydroboration. So if you take a boron and then add with a olefin, it will react with the, I think we are going to come back to the reaction in details, talking about the mechanism. Okay. So here what is happening, there is a hydroboration happening between the alkene and the boron to form successively. There will be 3 equivalent of the olefin getting consumed to form this trialkyl boron. Then the synthesis of the boronic acid. So the boronic acid can be synthesized once you treat a Grignard reagent or with a trialkoxy boron. It's actually a it's unstable, correct, because there is 2 phenyl with a 1 O-butyl group, and then once you want to stabilize it, then you use a chelating ligand which can chelate with both with the. So now what is happening, you can see you are generating with this chelating ligand. So this nitrogen has a lone pair, correct. So now the boron have this empty p orbital getting electron density and getting stable to isolate. Okay. So sometimes this type of boronic acids are not stable, as I mentioned. So to stabilize it, you have to use this type of ligand to, and then get them isolated. For the boronic acid, there are a lot of methods. I think it will be difficult to explain every single method here in this class. So my plan is to just talk about some of the early discovery, okay, for the synthesis. So if you have a organolithium, if you have I think it is written as MgBr, but if you have the RLi also, it will work the same way. That means if you take a phenyl lithium also, okay, or if you have a just alkyl lithium, like let's talk about n-butyl lithium or any RLi, okay, any other alkyl lithium if you take, and if you take with a trialkoxy boron, it could be a BOMe whole 3 I's. Okay. So now once you have this, what is going to happen? Now you can clearly understand here. So first, once the nucleophile comes, it attacks to the boron, it's R from minus, correct. From there, what is going to happen? One of the methoxy going to get out from here, and then once you treat with the HCl, okay, it is going to end up forming corresponding boronic acid. Okay, starting from the Grignard reagent or from the organolithium, it is end up forming a corresponding boronic acid. Okay, it can also happen that if you also recently there is method that if you have this corresponding aryl bromide, you can treat with, as I mentioned, this type of bis boronic acids under UV light. I think that can form a radical and also form the corresponding boronic acid. Okay. Again, then the boronic acid can be also act as a mild acid, as I said, depend, that also we are going to come back to that, because boronic acid can ionize to the water and forms the some sort of anionic tetrahedral species here. I think this is just we are talking about that the boronic acid can also give H plus. Again, these are depending on the sum of the boronic acid, we are going to come back to that boronic acid pK can change based on the structures. Okay, we are going to come back to some of the discussion as well. So here you can see here that if you have a boronic acid, and as I mentioned, now if you have a group like a nitro here, or you have a 2-3 nitro groups there, then what is going to happen? You are going to slowly, you see the pK getting increased from here. Like simple methyl boronic acids are not that acidic, but once you go to like something like a phenyl boronic acid starting and then if you go to like a paranitro, you are seeing a pK 7.1. Okay. So there is once you put a 2 nitro groups here, it will go even to close to 6. Okay. So we talk about the synthesis of the boronic acid, correct? Now one of the easy option to make the boronic esters. Okay. How you make a boronic ester? Of course, once you have a boronic acid, as I mentioned, one of the early methods is you make organolithium, magnesium, use this the BOMe whole 3, and then you add the HCl to coince the reaction that will generate the boronic acid. From boronic acid, if you take suppose you take a pinnacle or some sort of a diol here, 1,2-diol, it could be pinnacle, it could be something else. We are just showing here pinnacle, so there should be methyl here. And now both of this boronic acid, so now what is both of these OH going to get out from this boronic acid. There will be elimination of 2 equivalent of water to form this corresponding boronic ester. Okay. So generally in this reaction, using solvent also, you also try to use something called a molecular sieves. Okay. Because molecular sieves, what happens? The molecular sieve can take this water which is coming out from this reaction. Then there is another approach here. If you have the like a corresponding lithium or magnesium, if you have that, then you can also attack to this particular compound. Here you can see you have already a boronic esters here. You can see you already have a boronic ester here, and you also have a leaving group here. Okay. So you have kind of set up this isopropoxyl group for the leaving group. So once this type of R group going to attack here, you can think about this lithium magnesium as R minus, which can attack on the boron, and then followed by elimination of this part. From there get out the isopropoxy will come out, it will end up generating this corresponding boronic esters. That can be also done from starting from the organolithium reagents. Also you can also do from I think recently our group has shown that using the corresponding Grignard reagent, or if you use corresponding lithium, so it could be a a aryl, or if you have a alkyl lithium or magnesium, means I already talked about this could be organolithium or a Grignard reagent. If you treat with the B2Pin2, okay, directly if you treat with B2Pin2, as I said I think the B2Pin2 structure already shown before. So here what is going to happen, the nucleophile can attack here first. Okay. So if you have a nucleophile, it will going to attack here, going to form some sort of a structure like this. And then what is going to happen, you can clearly see there, once this is attacking here, now one of the boron is going to get out and trap with the water, and then that's how it is going to end up forming your corresponding boronic esters. And then there is a large number of methods to make in this type of boronic esters. I think there are large number of methods developed using light, which can avoid this using this organometallic reagent like this organolithium or organomagnesium. So one of the important method is as I mentioned before, if you use a UV light and using this aryl halide. If you use aryl halide, mostly mostly they use this type of, I think the fluoride, the chloride, bromide, everything kind of works, mostly works well with the bromide iodide. So using this, you can see this B2H4 as I mentioned, this boronic acid. So using them, they can able to make corresponding boronic acid or boronic esters. So if you treat them, so that means what is happening in this reaction, they mention that under UV light, they are generating this aryl radical. So aryl radical reacting with this, boronic acid or boronic ester to generate this aryl boronic acid or ester. Okay. Then there is another method where they use a pyridine, okay, starting from the same starting material, the aryl halide, but they use a catalytic amount of 4-phenylpyridine in presence of a alkoxide base, and they heat up at 85 degrees to generate the aryl boronic esters from there. Okay. Again, these reactions also have a very good yield, and they have a proposed mechanism that the alkoxide attacks first to the dibutene compounds, okay, and then to form some sort of a boronate complex. I am going to come back. So once you see the borons are trivalent, correct. Now once you have another nucleophile attacking on the boron, now this type of compound called as a boron as a 8 complex, because you can see it is no more a trivalent, correct. Once it become a tetravalent, now we call this as a 8 complex. So if you see in this 8 complex, once you have this 4-phenylpyridine, it is going to bound to the another boron which is electron deficient again, and then there will be a homolysis, there will be persistent radical formation and electron donor. This electron donor is very important role it is going to play. It is going to go for a single electron transfer to generate this aryl radical, which can couple with this persistent radical, okay, to transfer the boron from the pyridine to this aryl radical to form this corresponding aryl boronic esters. Okay. So there are even more methods, but we are not going to discuss them in this course. Okay. Then there is another important reaction I should definitely discuss about this reaction, which was discovered in around 1990s, that the reaction called a Miura borylation. So this is a tungsten metal catalyst reaction. So using palladium catalyzed reaction in place of the potassium acetate, dioxane as a solvent. If you start with the aryl bromide or aryl iodide or triplet, okay, that is your starting material, and then you are using this compound called the B2PIN2. Okay, you can say B2PIN2 or you can write this way. Okay. So in this type of B2PIN2 in place of aryl iodide and palladium catalyst, they can end up giving you aryl boronic esters. And how this reaction is happening, I think you have learned in my last class about the, I think we talk about some of the cross coupling, if you remember, in the organolithium and the Gigner, and also in the organocopper we talk about this Kumada coupling, then the Sonogashira coupling, correct, and then the Nigisi coupling. So here I am going to talk about this very similar step is the oxidative addition, correct. If you have learned organometallic chemistry, the first thing palladium 0, go for oxidative addition to palladium 2. Then what is happening? The base actually going for a transmetallation. So now we try to understand how this step is happening here. So what is happening, if you think about a boron, this bis boron compound, bis boronic ester compound. So once the nucleophile is attacking here, like you have this potassium acetate here, correct. So the OSE minus is going to attack here, correct. And now once this is attacking here, so this is the other boron is now, so now this is attacking this boron bond is getting weaker also. So this is allowing the other boron to be participate in a transmetallation reaction, okay, to transfer here, and then finally the reactive elimination can generate this corresponding boronic esters. So in this part I talk about the discovery of the boron, and I talk about the different type of the organoboron compound, like the boronic acid, the boronic ester, and then I talk about their synthesis, and I have shown you some of the the molecular orbital diagram of the diborans. Okay. And again here are the books you can download for this particular topic. And again thank you so much for coming to the class, and I am going to see you guys in the next class. Thank you.